All right, so in this section, we're going to talk about how the electrons are arranged in atoms. We've been talking about isotopes and protons and atomic number and mass number. So now we're going to talk about electron arrangements. So the electrons are located in different levels. Sometimes they're called shells. You may have learned this before. And the ones that we're really going to care about are the ones called valence electrons. So valence electrons are going to be the ones in the outermost ring. If you look here, this would be a valence electron. And these electrons are going to determine whether an atom reacts with other atoms. Most atoms on the periodic table want to have 8 of these, 8 valence electrons. And when they have 8, then their outer shell is considered full, and they're usually non-reactive. This is usually like your noble gases, like xenon and neon and all of those. So this one, for example, sodium, has 1 valence electron. Now, when they want to get to 8, there's kind of 3 options. They can either gain, lose, or they can share. So in the case of sodium, for example, and you'll learn more about this in chemistry, more so than biology, but it would have 2 ways to get to 8. It could either gain 7 more, or it could just lose this one, and then the shell underneath already has 8, because they sort of fill in order. So the easier pathway in the case of sodium is going to be to lose one. It's going to tend to lose a valence electron. On the other hand, something like chlorine has 7, so it's super close to having 8, so it would be more likely to gain an electron. And something like carbon has exactly 4, so it's not going to be very easy to gain 4 or lose 4, and so carbon would be very likely to share. So the number of valence electrons really is going to determine how it behaves with other atoms and what kind of chemical bonds it's going to make. So we did this one in class. So an atom that has 5 electrons in its valence shell. So this is really simple. You would just look at all of the atoms on the periodic table and look for one that in that outer ring has 5. And you'll notice nitrogen is an example of one. So 1, 2, 3, 4, 5. And interestingly, and you'll learn more about this in chemistry, phosphorus would also have 5. In fact, if you notice, there's a pattern in the periodic table. Everything in the first column has 1 valence electron. Everything in the second column is going to have 2 valence electrons. 1, 2, etc. So you'll learn that there's some patterns to this. So one with 5 would be nitrogen or phosphorus. And then one with a full valence shell, well, I mentioned they want to have 8. So neon and argon would be examples. But technically so would helium, even though it only has 2. And that's because if you remember in the activity that you did on the website, the first shell actually only holds 2. And since helium only has 1 shell, 2 would actually make it a full outer shell. But all the other rows of the table would want to have 8. Okay, so chemical reactions are what are going to make bonds between separate atoms. And this is when those valence electrons react with each other, like I mentioned. So a couple of things, just vocabulary you should know. The reactants are what are on the left side of the arrow, and the products are on the right. And then the arrow means yields. So in this case, you could see that the reactants would be here, and then the products would be over here. So this would be our products. This would be our reactants. And then the arrow would mean that this yields this. Also, very, very important, there's a rule, and you'll learn more about it again in chemistry, that's called the law of conservation of matter. It basically says that matter is never created or destroyed. And what that means is that the number of atoms that go in on the left side of a reaction should be equal to the number that come out on the right side of a reaction. So if we count up the carbons, hydrogens, and oxygens on the left, it should be the same number as the carbons, hydrogens, and oxygens on the right. So on the left side here, there are 6 carbons. There are 12 hydrogens. Notice these little numbers, these subscripts go with just the letter in front of them. And then for the oxygens, so this 6 in front multiplies by the 2 here. So this would be 12, and this would be 6 more. So there would be 18 oxygens. So carbon would be, going back, 6. Hydrogen would be 12. And oxygen would actually be 18. Now the law of conservation of matter basically says, since we don't create or destroy matter, on the right side we should have the same exact number of each of these atoms. And we do. So we have 6 carbons right here. we have 12 hydrogens, 6 times 2. And then if we add up all our oxygens, we have 12 plus another 6. We have 18 oxygens. What does happen in a chemical reaction, very important, is that the atoms do get rearranged. So on the left side, these are not the same molecules that we have on the right. This is actually glucose, which is sugar. This is oxygen, like what we breathe. This is carbon dioxide, and this is water. So our compounds changed, but the number of atoms didn't. And this is just another example. So this is the formation of water. So 2 hydrogen molecules react with 1 oxygen molecule, and then you end up with 2 waters on the right. Notice that the number of atoms is the same, but they've been rearranged in the chemical reaction. So a compound is a combination of 2 or more different elements put together into a particular chemical formula. The key here, make sure you know this for the test, is that they're different elements. So for example, H2O would be a compound, but O2 would not. Even though it's 2 atoms, this would actually only be 1 element. It's 2 oxygens hooked together, so this would not be a compound. HF would, NaCl would, and then Cl2 would not. So make sure you know that to be a compound, it's not just 2 elements hooked together, it's 2 or more different elements hooked together. And make sure you also understand that when you form a new compound in a chemical reaction, that compound will have different properties than what you started with. So for example, sodium is a metal. It's actually a shiny silver metal and it explodes in water. Chlorine is this toxic green gas that smells really bad if you smell like bleach. But sodium chloride is just table salt, perfectly safe to eat. So when these are combined in a chemical reaction, the product that you get has different properties than what you started with. And again, this specifically only happens when the valence electrons are either shared or transferred. Something either gives electrons to something else or they share electrons with each other. And this is just the example. This is chlorine, this is sodium, and that's sodium chloride. So there's 2 main kinds of chemical bonds. There's ionic bonds and then there's covalent bonds. And technically covalent bonds can be subdivided, and we'll talk about that in a second. There's also attractions between compounds. Those are called intermolecular forces, or IMFs, and we'll talk about that after we talk about bonds. So an ion is an atom that has gained or lost electrons. If the number of protons and electrons are not equal, you have an ion. You should have seen that on Monday. We did that activity on the website, and you explored that. You added electrons and took electrons away, and you should have seen charges form. When one atom gives electrons to another, the bond that's made is specifically called an ionic bond. And here's an example, and this runs pretty quickly, but if you look at the beginning, notice sodium has 1 electron. Chlorine actually has 7. So this has 1, this has 7 if you watch. And what ends up happening, see how this gets a positive charge and this gets a negative charge. So this one gave away its valence electron to the chlorine. This would now have a full outer shell, the sodium, because the shell beneath is full. And the chlorine would now have a full outer shell too, and the opposite charges hold them together. What kinds of things make ionic compounds? It's usually a metal and a nonmetal, because typically nonmetals only have 1 or 2 valence electrons, and nonmetals usually have 6 or 7. They're very close to having 8, so one really has the ability to steal from the other. They're all solids at room temperature, like sodium chloride is an example. And in our bodies, they form ions in water. So this is your electrolytes. This is why your sweat, for example, tastes salty. So in your body, these would break up into things like sodium ions, chloride ions, magnesium ions, calcium ions. And they're really important for things like your blood pressure, your water balance, muscle contraction, your nervous system. These ions are really, really important. And again, we call them your electrolytes. Sometimes. We're going to skip the little video here. On the other hand, if atoms share, then they form what are called covalent bonds, which is going to look a little bit different. Covalent bonds, instead of one stealing from the other, they both share the outermost electrons. Unlike ionic compounds, they're not all solids at room temperatures. They can be solids, liquids, or gases, and they're usually 2 or more nonmetals. So a lot of the things we're going to talk about in our next chapter, like water, sugar, proteins, fats, your DNA, your muscle, your hair, those are typically covalent compounds. They have a lot different properties than ionic compounds. And the smallest unit of a covalent compound is called a molecule. Now, these can be subdivided into polar and non-polar. So non-polar is where the electrons are shared equally between the two. So neither one is really pulling harder on the electrons than the other. Water is an example of what's called a polar covalent bond, which sounds like it has to do with cold, but it has nothing to do with cold. And that has to do with one of the atoms being much more what's called electronegative than the other. So if that happens, what happens with water, and we'll cover this in another lecture, oxygen has 6 and it just wants 2 more. And these 2 itty bitty hydrogens, they each have 1. And what ends up happening is the hydrogen shares with the oxygen, but the electrons sort of hang around the oxygen more. So, because electrons are negative, the oxygen gets what's called a partial negative charge. This is the symbol. It looks kind of like a figure 8. And the hydrogens get a slight positive charge. It would be sort of like if we were sharing a candy bar. If I broke it in half and gave you exactly half of it, that would be like a non-polar covalent bond. We each get exactly half, and we're sharing evenly. On the other hand, if I broke off a quarter of it and gave it to you and I ate the rest, that would be like a polar covalent bond. And I would be the one that's more electronegative because I got 3/4 of the candy bar. Technically, I still shared. If I just grabbed the candy bar and run, that would be an ionic bond. I took all the electrons and I ran away and I didn't give you any. And just to summarize, last slide for today, here's non-polar covalent. See how they're evenly sharing. Imagine the electrons are evenly going around both. This is a polar covalent bond. So the chlorine, they're kind of hanging around the chlorine more, and that's what the blue is showing, which gives it this partial negative. And the hydrogen has a partial positive. You might wonder why there's a positive. That's because, remember, these still have protons in the middle. So if you have more protons than electrons, you end up with that slight positive. And then here's your ionic. The chlorine literally steals the electron from sodium. This has a plus charge, and this has a minus charge.